Good morning. Myself, Vijay Krishna, belongs to the Department of Mechanical Engineering. So, in the video lecture, I'm going to deliver the subject Thermodynamics, Module 1. So, this video lecture of the subject Thermodynamics consists of different module. So, today, let's see the Module 1. So in the module 1, we'll see introduction to the course and why need to study the subject thermodynamics. The thermodynamics, what are the applications available and approach. So this is a subject, so how to approach various types of system and units. So units plays a major role in the problematic subject. Since thermodynamics is a problematic subject, the units also is very important. So next we'll see what are the properties of system. Next, state and equilibrium, process and cycles, steady flow process, and the first law in the thermodynamics is the zeroth law. So that also we are going to see. And last we'll see the problem solving techniques, because whenever we solve the problem, there is a sequence of procedure is available. So that approach only the student should implement. So we'll see what are that. So in first introduction to the course, so in the branch of mechanical engineering, if you see, it is classified under three major categories: design, thermal and manufacturing. So the subject thermodynamics comes under the stream thermal. So more or less thermodynamics and the word thermal relates that heat. So more or less we are going to see heat parameter only in the subject thermodynamics. So under subjects of thermal stream, we are having various subjects like thermodynamics, fluid mechanics, thermal engineering, heat and mass transfer, gas dynamics, and space propulsion. So under this, thermodynamics is the first and foremost subject. So in the BTech syllabus, under thermal stream, students will learn thermodynamics is the first subject. So if the students study thermodynamics only, then only they can go for a thermal engineering, heat and mass transfer, gas dynamics subject. So obviously thermodynamics is the prerequisite for remaining subjects like thermal, heat and mass transfer, gas dynamics. So another stream in the thermal, we are having fluid mechanics. Thermodynamics. So thermodynamics, first of all, we should know the word what is thermodynamics means. So this thermodynamics itself we can split into two. One is thermo, another one is dynamics. So the word thermo comes from the Greek word thermi, T-H-E-R-M-E. So from that only they have derived the word thermo. So it is nothing but the meaning heat. Next is dynamics. So the dynamics also comes from the Greek word dynamis. So the meaning for dynamics is the power. So in the subject thermodynamics, we're going to see how the heat is converted to power. So the most general introduction to thermodynamics is nothing but how this heat we can convert to power. So student also in their lower classes, they might have seen the law of conservation of energy. That is, energy can neither be created nor destroyed, but it can be transformed from one form to another form. So likewise, here also we are focusing on the energy conversion. So more focusedly, we are going to see how heat is converted to power. So why need to study thermodynamics? So before starting any subject, students should essentially know what is the need to study the subject thermodynamics. So it is a very fascinating subject that deals with the energy, and we can also say that it is a science of energy. This thermodynamics concept we can apply from microscopic organism, household appliances, to the vehicles, power generation system. So more or less this can be applied from minor to major also. So this subject gives about the energy and the mechanism of energy balance, energy conversion and conversion efficiency also. For example, we are having a solar collector nowadays we are using. So in the solar collector, if you see the solar energy is converted to heat energy. So we'll focus how this energy is converted. So how much energy is utilized. So how much energy is wasted. So these analyses we can able to do in the subject thermodynamics. So once we know the basics only, we can proceed towards the energy analysis in the thermal related systems also. So applications of thermodynamics. So in the previous slide also, in order to analyze the thermal related system, we ultimately everyone should know the basics of thermodynamics. So that's why we are studying the subject thermodynamics. So normally the applications of thermodynamics, we can use it in from small objects to the larger system also. Same thing. For example, we can apply the thermodynamics concept in the pressure cooker also, because in the pressure cooker we are putting rice and we are boiling it, and we can see that we are supplying the energy. So how much energy is utilized for boiling the rice and how much energy is wasted. So these analyses also we can do in the home household objects like a pressure cooker, and obviously water heater also we can implement this application, because with the help of electrical energy it is converted to a heat energy, so that the water temperature is increased. So how the energy is transformed, and how much energy is utilized and how much energy has been lost. Okay, so more or less there is a loss of energy. So this loss of energy we have to minimize. So we know that researchers also proceeding lot of focus on how to minimize the losses. So these losses and all we want to calculate, means we have to know this subject also. So this analysis we are doing in automotive engines, rocket, jet engines, nuclear power plant, and conventional is steam power plant and solar collector also. Next one is under applications of thermodynamics itself, we are going to see more detail is internal combustion engines. So internal combustion engines are broadly classified into two types, petrol engine and diesel engine. So more or less we have to know what is the difference between a petrol engine and diesel engine. So petrol engine will be having a spark plug and diesel engine will be having a fuel injector. And another difference is that in the petrol engine, uh, air and fuel are mixed together, and the homogeneous mixture of air and fuel will be sent to the cylinder in the case of petrol engine, whereas in the diesel engine only the air will be sent during the intake stroke. So these are the major difference between petrol engine and diesel engine. Next thing is that in the diesel engine, if you see, there are four major processes are available: intake stroke, compression stroke, power stroke, and exhaust stroke. So these stroke we'll see clearly, and we'll see how the subject thermodynamics have implemented in the internal combustion engines. That also we'll see. So we know that in the internal combustion engines, the major parts are we are having two valves, inlet valve and exhaust valve. We are having a piston, connecting rod, a crankshaft. So these are the major components available in the internal combustion engine. So first, what happened in the intake stroke for the diesel engine? So first, the inlet valve will be open, the exhaust valve will be closed. So when the inlet valve open, what happened? The piston will be at the top dead center. So due to the opening of the inlet valve, the fresh air will be entering into the cylinder. So due to this, the piston moves from top dead center to the bottom dead center. Okay. So next is the compression stroke. In the compression stroke, what happened? Again, the piston moves from bottom dead center to the top dead center. Here the air is compressed. Okay. And one more thing, both inlet and exhaust valve will be closed here. And here we are implementing the compression process. So due to compression, the pressure and temperature of the air will be increased. So once the piston reaches the top dead center, the next process, that is power stroke, will be carried out. So once the piston reaches the top dead center, and because of the high pressurized and temperature air, will be having a fuel injector. So from the fuel injector, the fuel will be sprayed. Okay. So what happened once the fuel is sprayed, the combustion process will be initiated. So the combustion process nothing but it is nothing but a release of heat energy. So due to this combustion effect, what happened again? The piston comes from top dead center to the bottom dead center. After the combustion, we'll be having a exhaust gas. So this exhaust gas we have to give to the surrounding. So what happened again? The exhaust valve will be open. So again the piston moves from bottom dead center to the top dead center. So the gas will be expelled to the surrounding. So more or less, if you see in the diesel engine, during the intake stroke, inlet valve will be open, exhaust valve will be closed. In the compression process, both inlet and exhaust valve will be closed. And power stroke also, both inlet and exhaust valve will be closed. And in the exhaust stroke, inlet valve will be closed and exhaust valve will be open. So let's see how the thermodynamics concept is implemented here. So we know that thermodynamics is the subject which deals with energy. So we are having a sequence of energy transformation. First, we are having a chemical energy. That means we are using the fuel diesel. So diesel normally consists of hydrogen and carbon. So this chemical energy of the fuel is converted to a heat energy. Okay. So that's why the combustion process is liberated. Next, what happened? This heat energy is converted to a mechanical energy. So what happened? The piston moves from up and down. That is a reciprocating motion. That reciprocating motion is converted to a rotary motion with the help of a crankshaft. So in between we are having a connecting rod. So there is a sequence of energy from chemical to heat and heat to mechanical. So if you see heat energy to mechanical energy, so we'll be with the help of thermodynamics we can able to calculate how much amount of energy is supplied. That parameter we can able to find. And next thing is that how much energy is utilized. Okay, so how much energy is utilized means how much energy is converted to mechanical and what are the losses. That analysis we can able to do in the subject thermodynamics. And we can able to find the energy conversion efficiency also. So these analysis we can able to do in the diesel engine. Another example we can say that in the consider a house, in that we are implementing a solar collector, and we with the help of solar collector we are going to heat the water. That water we can use for domestic application. So we'll be passing the cold water, and with the help of solar energy we are getting a heat. So this cold water will be converted to a hot water. So here also we can do the analyzing with the help of solar energy, how much energy we have recovered. So to convert cold water to the hot water. So how much energy is utilized and how much energy is wasted. So these parameters and all we can able to do. Next one is types of approach. Normally in the thermodynamics we are having two approach. One is a macroscopic approach, another one is a microscopic approach. So the word macro itself shows that it deals with the large, and the word microscope tells that it deals with a small. Okay, so macroscopic approach deals with the whole system. Okay, it doesn't worry about the individual component, whereas microscopic approach focus on the individual component. That means the individual particles. The other name for a macroscopic approach is the classical thermodynamics. The other example for microscopic approach is the statistical thermodynamics. So simple example I can like to share here is that we are having a class of 60 students. If we are finding the 60 for all the 60 students, if we find the pass percentage, then it is a macroscopic approach. If we find the pass percentage of the single student, then we can call it as a microscopic approach. Like that also we can relate to this types of approach. And another example we can say that, for example, we are having a petrol. That petrol we are converting to the heat energy. So we'll be seeing 1 liter of petrol, how much it is converted to a heat energy. That is a macroscopic approach. If you see in the microscopic approach, the petrol obviously consists of n number of individual molecules. So if you analyze from one molecule how much heat energy is liberated, then it is known as a microscopic approach. System. So why we are having the term system? Because obviously we are going to analyze the thermal related systems like internal combustion engine, steam power plant, etc. So that's why we have bring the term system. So system is nothing but a quantity of matter. Okay, so whatever in the universe exists as a matter, we can consider as a system. Simple example, we can say human body is also a system. The mobile phone we are using, that is also a system. Okay, and laptop, everything is a system. Okay, next one, surrounding. Okay, so the mass or region outside the system is called its surrounding. Everything that means outside the system, we call it as a surrounding. Why we are considering the parameter surrounding? Because obviously there will be energy interactions between a system and surrounding. So we have to differentiate the system and the surrounding. So for that we are having an imaginary surface that known as a boundary. So boundary is the one which separates the system and surrounding. Okay, so it is an imaginary one. Types of system. So we have seen that a system is nothing but quantity of matter. So under this types of system, we are having three categories: closed system, open system, isolated system. First we will see the closed system. So the major introduction to closed system is that in the closed system there will be a energy transfer, but there won't be a mass transfer. That means there no mass transfer takes place, but only energy transfer takes place. So in the slide also we can see that we are having a gas enclosed in the piston cylinder. The mass remains constant only. Okay, so mass won't be coming out, it won't interact with the surrounding. In the next below slide also we can see that we are having a gas enclosed in the cylinder. Here they had given the notation mass equal to 2 kg and volume equal to 1 meter cube. So we are giving the energy. So by giving the energy, what happened? The piston, that means the gas expand. So due to the expansion, the volume is increased. So the volume is increased from 1 meter cube to the 3 meter cube. So we can see that there is an energy transfer, but the mass remains in the system itself. It is not coming out. Okay. So the other name for closed system is the control mass. Next one is the open system. So open system, here what happened? Mass transfer will take place and energy transfer also takes place. The best example we can tell water heater also. So we are having a water heater. Initially we are supplying the cold water. We are supplying the energy. By supplying the energy, the temperature of the cold water is increased. We are getting a hot water. Then we are collecting the hot water. That hot water we are using for domestic applications. So here the cold water is supplied to the system. Here let us consider water heater as a system, open system. The cold water is supplied and we are collecting as a hot water. So here the mass we are getting out. Now obviously the mass is coming out from the system. So energy we are transferring in terms of how we are transferring electrical energy to a heat energy. So in the open system, there will be a transfer of both mass as well as energy. So the other name for open system is a control volume. Last system is the isolated system, but obviously the isolated system not exist in the universe. So because why we are telling there won't be any no transfer of mass or no energy in that. Okay. Units. Units is the most important for the student, because if the student well versed in the units means he can easily tackle the problems, and more or less we have seen students used to make mistakes in the units also. So first itself we have to give some introduction to the units, and we have to tell to the students what is the importance of units. Okay, because if they have strong in the units, surely they will clear the problems. Okay, so the first units we are going to see the energy. Since we know that thermodynamics deals with the science of energy, uh, we'll see the energy, and we are having a heat. Okay, under energy we are having heat and work, and internal energy and enthalpy. So next module and all we'll see what is internal energy, what is enthalpy. For all those things, the unit is going to be same. Either it will be kilojoule, or it going to be a joule, or it is going to be a Newton meter. So 1 kilojoule equal to 1000 joule. 1000 joule is nothing but we can write it as a 1000 Newton meter also. And we can represent with per unit mass also. That means energy we can denote with per unit mass. So 1 joule per kg equal to 1 meter per second square by uh, 1 joule per kg equal to 1 meter square by second square. So this unit conversion and all will be using in the steady flow energy equation later. 1 kilowatt hour equal to 3600 kilojoule. Sometimes in the problem they will give kilowatt hour. So obviously we have to know how to convert kilowatt hour to 3600 kilojoule, and 1 calorie equal to 4.184 joule. Next we will be using force. We are using that, we know that 1 Newton equal to 1 kilogram meter per second square, mass 1 kg equal to 1000 gram, 1 metric ton equal to 1000 gram, and density and all will be using the unit is kg per meter cube. Power, heat transfer rate. So obviously since we are focusing on the subject thermodynamics heat, so the whoever studies the subjects, ultimately they should not mismatch the term heat and heat transfer rate. Okay, heat is different and heat transfer rate is different. Heat unit is kilojoule, whereas heat transfer rate is will be calculating everything based upon the time. That means per second how much energy is liberated. Okay, so everything with respect to time if you are considering, then we call it as a heat transfer rate. So 1 watt equal to, we know that 1 joule per second. Then 1 kilowatt equal to 1000 watt, and we should know 1 HP equal to 746 watt. Next one is the specific heat. Under the specific heat, we are having two types of specific heat also: specific heat at constant pressure, specific heat at constant volume. The unit is kilojoule per kg Kelvin, or we can tell kilojoule per kg degree Celsius. That means we are having a 1 kg of mass. Okay, it has the temperature of 25 degrees Celsius. So if you raise the temperature to 26 degrees Celsius for the 1 kg of mass, so how much energy is given out? So that is known as a specific heat. So that's why we are having the specific heat unit as a kilojoule per kg Kelvin. Next one is pressure. So in the thermodynamics subject, very often we'll be using the parameters: temperature, pressure, volume, density. Okay, so in the problems also, if you see in the thermodynamics subject, the students are asked to find out more or less temperature, pressure, volume, density. So if you know these parameters, they can find energy. Okay, so 1 Pascal equal to 1 Newton per meter square, 1 kilopascal equal to 10 power 3 Pascal. Sometime in order to give the problem in terms of pressure unit in terms of atmosphere also. So 1 atmosphere equal to 101.325 kilopascal. Then this kilopascal we can convert to bar also, that is a 1.01325 bar. Uh, Normally we are not using a 760 mm of Hg, but we have to know 1 mm Hg equal to 0.1333 kilopascal. Temperature. So more very often we'll be using the unit temperature. Uh, will be have to convert, it will be given in degrees Celsius, so they have to convert to Kelvin. So whenever it is given in degrees Celsius, we have to add plus 273, then we'll be getting Kelvin. We have to know the what is the temperature relations between Rankine and Fahrenheit. So if it is given in Fahrenheit, if we had plus 459, we'll be getting in terms of Rankine. So how to convert next third one, Kelvin to Rankine? So for example, we are having 273 Kelvin. If you multiply with 1.8, we'll be getting Rankine. Next one, degree Celsius to degree Fahrenheit. So we are having a 100 degrees Celsius that we have to convert to degree Fahrenheit. So that 100 degrees Celsius we have to multiply with 1.8. Then after that we have to add plus 32. So this is a general unit conversion. Properties of a system. So for a, we have seen the system. System is nothing but a quantity of matter. Then under the system we have seen types also, open system, closed system. So obviously all the system will be having a property. Okay, so the most familiar properties for the system is pressure, temperature, volume, mass, etc. So there are lots of properties are available, but we have to categorize these properties. So for that we are having a term intensive or extensive. So properties are classified into two categories, intensive property or extensive property. So intensive property. So intensive property is independent of the mass of the system. Okay, these properties will not influence by the mass. So example, we are having a temperature, pressure and density. Extensive properties, these properties will be depend on the mass of the system. So these properties will be influenced by the mass. Example, we are having a total mass, total volume, total momentum, etc. Next, we are having specific properties. That is, we are having extensive properties that is depend upon the mass. So if extensive properties, if we consider per unit mass, then we call it as a specific properties. For example, we are having a volume that is denoted by a capital V. So if we consider per unit mass, then we call it as a specific volume. Similarly, we are having energy. So per unit mass, if you have, we are having E by M, then we call it as a specific total energy. So more or less for the specific properties, we'll be having units like meter cube per kg, kilojoule per kg. So in the denominator, we'll be having the unit as kg. State. Okay. State is a one of the definitions we are having in the thermodynamics. So in the human life also, when we come morning, we'll be having a state will be higher, we'll be having a high energy. So in the afternoon, our energy will decrease, and in the evening, more or less, will become tired due to our work. So likewise, state. Okay, so because of certain process, there will be a changes in the state. So whenever there is a change in the state, the properties also will be changing. So for example, if we are having a state 1, in the state 1 it will be having a fixed values only. Here we can see that in the first cylinder we are having M equal to 2 kg, temperature equal to 20 degrees Celsius and volume equal to 1.5 meter cube. So what happened? If we go for any process, because of that, now we can see in the state 2 the volume is increased to 2.5 meter cube. So at a given state, all the properties of a system have a fixed values. So if you go for any process, there will be a change of state from 1 to 2. Next one, equilibrium. So thermodynamics also deals with the equilibrium state. So the word equilibrium implies a set of balance. Okay. So under this thermodynamics equilibrium, we are having various types: thermal equilibrium, mechanical equilibrium, chemical equilibrium. So for example, we are having a system. That system is satisfied thermodynamic equilibrium, means that should satisfy thermal equilibrium, that should satisfy mechanical equilibrium, and finally chemical equilibrium. So first one is thermal equilibrium. So from the word thermal equilibrium itself, we can say that it is a temperature. So thermal equilibrium means the temperature will be same throughout the entire system. Okay, so for example, in the picture we can see that let us consider we are having a different gas molecules. The gas molecules occupies a different temperature, 20 degrees Celsius, 23 degrees Celsius, 30 degrees Celsius, 35 degrees Celsius, like that. But after the energy interactions, we can see in the next picture, all the gas molecules occupies the same temperature of 32 degrees Celsius. So if a system has a uniform temperature throughout, then we can call it as a thermal equilibrium. Mechanical equilibrium. So in the mechanical equilibrium, the pressure should not change. The pressure should be same at any point in the system with respect to a time. So thermal equilibrium means temperature should be uniform. Mechanical equilibrium means the pressure should be uniform. Last one is chemical equilibrium. In the chemical equilibrium, the chemical composition does not change with time. So that means there should not be no chemical reaction should not take place, because if there is a chemical reaction means obviously there will be a change in the chemical composition. So the system, if it is in the chemical equilibrium, means the chemical composition should not change with respect to time. So thermal equilibrium means temperature should be uniform. Mechanical equilibrium means pressure should be uniform, and chemical equilibrium means the chemical composition should not change. Obviously there should not be no chemical reactions. Okay, so if these equilibrium exist in the system, means then we can call it as a thermodynamics equilibrium. Next one is a process. So we are having a one equilibrium state 1. So it follows a certain process and it attains the next equilibrium state 2. Okay, so whenever a system undergoes one equilibrium state to another equilibrium state, then we can call it as a process. We are having various types of process, like a constant volume process, constant temperature process, constant pressure process, isentropic process. So these processes are available. So next one is the path. Path means we are having a state 1 and state 2. So in order to attain the state 2 from state 1, we'll be having a path function. Okay, the series of state through which the system passes during a process is called the path of the function. Quasi-static process, or we can call it as a quasi-equilibrium process. First of all, quasi-static process is the ideal process. Okay, but in the nature we cannot say all the process is the quasi-static process. So it is an idealized process. And second thing, it is a very slow process. Okay, so what is quasi-static process? For example, we are having a state 1, it moves to a state 2. In the state 1, it has a pressure of 30 bar. In the state 2, it reaches the pressure of 35 bar. So state 1 30 and state 2 it has a 35 bar. So for attaining that 35 bar, rapidly it won't reach 35 bar. So it goes a very small value. For example, when next step it will be having a 30.001, next it will be having a 30.002, then it will reach 31. Like that it proceeds. So For attaining the 35 bar, immediately it won't reach. Okay, it is a very slow process. So in the picture also it shows that we are having a quasi-equilibrium and a non-quasi-equilibrium. So quasi-static equilibrium means normally the compression process will be very slow. Then only this process can take place. Okay, if you go for a very fast compression, there will be a rapid changes in the properties value, and there will be a non-quasi-equilibrium only will takes place. Cycle. So first itself we have seen as an example internal combustion engine. We are having a different process. So we are having intake, compression, power and exhaust. Again it comes to intake. So that is also an example for cycle. More or less cycle will be in the cycle, if you see, the initial and final states are going to be identical. Steady flow process. Okay. Steady flow process means we are having a fluid properties with respect to time it won't change. Okay, for example, we can see in the slide at 1 p.m. we are having a system. The mass is also entering and the mass is also coming out, and it has a temperature 300 degrees Celsius, 250, 200, 150 like that. Again, if you see for after 2 hours, that is 3 p.m. In the system will be having the same temperature will be having 300, 250, 200 and 150, even though the mass is entering and mass is leaving. So that means the fluid properties will not change with respect to time. Okay, that is known as a steady flow process. Whereas thermal equilibrium means we'll be having in the system will be having a same temperature throughout. Steady flow process means with respect to time will maintain a same temperature. At one point we are having 300, another point we are having 250. After 2 hours also we'll be having a same 300 and 250. Then we can call it as a steady flow process. Whereas thermal equilibrium means after some time throughout the system will reach the same temperature. Zeroth law of thermodynamics. So in the subject thermodynamics, the first law is the zeroth law. So two things we should know with respect to zeroth law. Zeroth law speaks about the thermal equilibrium, then it speaks about the temperature also. So what is zeroth law states that we are having two bodies. Okay, so let us consider iron and copper. So iron at the temperature of 150 degrees Celsius and copper at the temperature of 20 degrees Celsius. So after some time what happened, there will be a transfer of heat from higher temperature to a lower temperature. So in the natural phenomena, if we see, there will be a transfer of heat from higher temperature medium to a lower temperature medium. Okay, because from lower temperature to higher temperature, heat cannot be transferred. Okay, if we want to transfer the heat means we have to go for a special type of devices. Okay, so heat always transfer from higher temperature medium to a lower temperature medium. So likewise, we are having a iron at the temperature of 150 degrees Celsius and copper we are having 20 degrees Celsius. So from iron the heat will be transferred to the copper until the thermal equilibrium condition attains. So finally you can see that iron will be having 60 degrees Celsius, copper also will be having 60 degrees Celsius. So once the system attains the thermal equilibrium, there won't be a transfer of heat. Okay, so now these two bodies attains the thermal equilibrium condition. Now we are bringing another body, third body. So finally what happened, all these three bodies will attains the same temperature. Okay, so zeroth law states that we are two bodies are in thermal equilibrium with a third body, then they are also in thermal equilibrium with each other. Okay. Last thing is that problem solving technique. So why this we have to tell to the student, because more or less we have to follow the sequence of procedure, then only we can able to solve the problems in a clear manner. Or else if you want to apply this procedure, the problems looks very clumsy. So If they remember this sequence, they can, in a clarity manner, they can solve the problems. So there are steps are available. The first step is the problem statement. So whenever problems are given, students should read the problems at least twice or thrice, because they can make any mistake with values or units. So they have to read the problems twice or thrice. Then from the problems they have to take down the data. The data they have to clearly write on what things they are asked to find. Next is to find. In that what they are asking in terms of per second, per kg. So these things and all they have to clearly mention in the first itself. That is a problem statement. So first, what are the data given in the problem? Next, what to find, they have to identify. Step 2 is the schematic. So whatever questions given, for that they can make a schematic diagram. For example, if they are giving a turbine, the mass is entering and mass is leaving, they can draw a rough sketch, so in that they can mention the parameter value, so that by looking into the diagram, they can give some, they can get some ideas also. So diagram will be very helpful. Step 3 is the assumptions and approximations. So whenever we solve the problem, since we are focusing the subject theoretical approach, so what are the approach we have to, what are the assumptions we have to follow? For example, if you are implementing a steady state condition, means that also they have to consider whether they are considering as ideal gas. So what are the assumptions we are considering for the problem? That also we have to make a note of it. Next one, physical laws. So what are the physical laws will be available that they can interpret, so that they can find the properties also. So step 1 is the problem statement, and step 2 is the schematic, and step 3 is the assumptions and approximations, and step 4 is the physical laws. Step 5 is the properties. So using the laws, whatever unknown properties are available, they can find that one. Sometimes the properties they can able to find with the relations or table also. Step 6 is the calculations. So calculation is the most important. In that the units should be, they have to implement very properly. For example, we are having PV equal to MRT. In that we have to find mass. For example, if we are taking pressure in terms of kilopascal, the R should be in terms of kilojoule per kg Kelvin. We should not take joule per kg Kelvin. In that case, the unit will not satisfy. Next case, pressure we are taking in terms of Newton per meter square, then our unit should be in terms of joule per kg Kelvin. So whenever they are making the calculations, they have to use the correct quantities, and they have to check whether the units are satisfied. Last condition is the reasoning, verification and discussion. They can verify, and they can relate due to the pressure how the system is affected, due to temperature variations how the system other properties are affected. That logical reasoning also they can do. So if they follow this procedure, they can solve the problem in a very clarity manner, or else it becomes clumsy only. So in order to avoid that, they can follow the sequence of steps in the problematic subjects. So the problem solving technique always step by step approach. Okay, that only simplify the problems. So in the picture also it shows that if you follow the some other method, it becomes a hard. So if you go by step, easily we can solve the problem. Thank you.